Chapter 10, Learning Outcomes 10.1 and 10.2. Describe how and why z-transforms and Laplace transforms are related. Describe how and why discrete Fourier transforms and z-transforms are related. Discrete transforms are designed for the discrete time, and they're very similar to Laplace transforms. So let's look at what we have for continuous time, which you already know, and compare it to how it works in discrete time with a z-transform. In continuous time, a differential equation is the most common way to express an input-output system, your LTI system, which we use mostly in this course. On those differential equations, we use a Laplace transform. The Laplace transform has the analysis integral x of s equals integral minus infinity to infinity x of t e to minus st dt. We can use that Laplace transform, maybe not directly the integral but from the tables, on this differential equation, and it will produce sy of s plus y of s equals 3s x of s minus 2x of s. The derivative operator becomes an s times our Laplace transform. We use linearity with both the additivity and the scalability components of it in our transform. To get our transfer function, h of s, which is the ratio of y of s and x of s, we collect our y terms, collect our x terms, and divide. We wind up with h of s is 3s minus 2 divided by s plus 1. Now let's see how the same thing works on a similar system in discrete time. In discrete time, our input-output equation would be a difference equation. You use these in Chapter 2. You found the impulse response from these. We did all sorts of other things with them as well. We have our output variable at various discrete time units, square brackets, n instead of t. In discrete time, we use the z-transform. The analysis equation for a z-transform is x of s equals a sum for n equals minus infinity to infinity, x of n, z to the negative n. Compare them. They're very similar. Z is also a complex variable, just like s is. Instead of an integral, we have a summation because we're talking about discrete instead of continuous, but that goes from negative infinity to infinity. We have our time function x of n instead of our time function x of t. Then the big difference is instead of e to the minus st, we have z to the minus n. And we'll compare those two. But you can see that they're very similar in form. From the tables, y of n transforms to y of z. A time delay is a shift, z to the negative 1, y of z. Linearity still applies where we have addition. Linearity still applies with the scalability 3. To find the transfer function, we likewise group our y's, group our x's, and then divide. H of z is y of z over x of z, just like h of s is y of s over x of s. The big difference is that we have z to the negative 1's instead of s's. Let's look at these transfer functions. In continuous time, we can invert h of s to find h of t. Because the order of the numerator is the same as the order of the denominator, we first need to apply a long division to get into a constant plus a proper fraction. The constant will invert to 3 delta of t, and our fraction, our proper fraction, will invert to minus 5, linearity, e to the minus t, u of t. Don't forget the u of t. In discrete time, we likewise want to invert our h of z to find our h of n. Similarly, we need to have a proper fraction, but proper is a little bit different now. The order of the numerator has to be lower than the order of the denominator, but these z to the minus 1's can be confusing. Notice that in the denominator, the order is 0, and now in the numerator, the order is negative 1. Negative 1 is lower than 0. 3 has a very similar inverse transform to what we saw in continuous time with Laplace. It inverts to 3 delta of n. Notice it's delta of n instead of delta of t. The inversion of this fraction is a little bit more complicated. We'll work on that in a future video, and you should look at your tables and you can figure it out. But get the general idea here. Linearity, the minus 5 comes out. If you look at your tables, there's a 1 over 1 minus alpha z to the negative 1, and for this fraction, alpha is negative 1. Because of this z to the negative 1 in the numerator, it's really multiplied out in front, just like the negative 5 is multiplied out in front. This z to the negative 1 is time shift, similar to what you had in chapter 9 with Laplace, and in chapter 4 with Fourier transforms. This z to the negative 1 says time shift every n that occurs. Our 1 over 1 minus alpha is alpha to the n u of n. This now says take each of those n's turn into n negative 1, alpha to the n minus 1 u of n minus 1. Again, alpha is negative 1. Let's also look at these analysis integrals a little bit more. For Laplace, x of s is integral, negative infinity to infinity, x to t, e to the negative st dt. Let's look at this e to the negative st. We saw the e to the negative j omega t for the Fourier transform, so we know this is really the key part of our transform function. Our z transform with that summation has the z to the negative n. We know from chapter 9 that if s equals j omega, our Laplace transform turns into a Fourier transform. So let's make that substitution, e to the negative j omega t. We can discretize this by setting t equal to n times t. N is our count, our discrete variable. T is our sampling period. Then our exponential becomes e to the negative j omega nt. We can rearrange this, taking the property that e to the a times b is e to the a raised to the b. And we get e to the j omega t raised to the negative n. Let's go back to our z transform. And look, we've got that z to the negative n. Therefore, we can conclude that e to the j omega t is a variable z. If we discretize in a sampling period of t equals 1, because we're taking n equals 1, 2, 3, 4 as a variable when we have our discrete x of n, our t is 1 and our exponential is e to the j omega. So z equals e to the j omega. We'll use this in later chapters, but looking at this, this has a magnitude of 1 and a variable angle. That's our unit circle. The unit circle plays a very important role in z transforms.